As we jump into applying the concepts of Newton's laws to physical systems, we're going to start with straight line motion. And by doing this, what we can do is we can drop the vector notation for a little while and only deal in scalars. And so just to be sure we're all on the same page, let's define what we mean by straight line motion. So I'm going to define a wall here, and this is going to be our origin of point O, and then the reference frame I'm going to define, and we always define our reference frames in this class with these dashed lines. This will be our inertial reference frame. We have a particle that has mass m that's moving in a straight line along what we would say is this basis vector. We can even put a basis vector here, e sub 1. So it's moving along this line, and it has a force that's applied to it, F of x. And we're going to use x here because in our straight line motion, we're dealing with this horizontal direction, which we like to call x. And so then let's define an x, which is saying that as x increases, it's moving away from the origin, and if x decreases, then it's moving toward the origin. So we're allowing this particle m, or this particle with mass m, to move along a straight line. As x increases, it's moving away from O. If it decreases, it's moving toward O. And so now with this idea of an increasing coordinate x or decreasing coordinate x, what we've now defined is x dot. So x dot is the change in position of x, and using Leibniz notation, it's just dx dt. Or if we do one more time differentiation of this, x double dot is equal to dx dot dt. So it's the time differentiation of the speed of x. And so also keep in mind that the coordinate x and its time differentiations are all functions of time. So that's why we can do a straight differentiation. Dx dt is equal to x dot, or dx dot dt is equal to x double dot, the acceleration. Now, in example 2.1, we're going to solve the equation of motion for the state of the system. That's going to be the position and the speed. Recall what the definition of state is when there are no forces applied to the particle. So this means that Fx, our force applied to the particle, is equal to 0. There are no forces. So when we apply this to Newton's second law, our equation is Fx is equal to m and its acceleration, so it's x double dot. And if our force is equal to 0, then by default our x double dot is equal to 0. Now this isn't a trivial solution, but instead it tells us that x double dot is equal to 0. And you know how to interpret this. This means that that particle is either at rest or it's moving at a constant speed. But now that we're in dynamics, and now that you have a foundation that's beginning through engineering, and now that you've taken differential equations, then what should be happening are these are alarms going off in your head that says, holy cow, this is a second order ordinary differential equation. And we see that because it's x double dot, that's our second order term. It's equal to something. It doesn't matter what it's equal to. This is always a second order differential equation, and it's an equation of motion. We can use this equation of motion to then find the state of the system at any point in time, which is x and x dot. And this is a nice simple system that we can solve simply by integrating. So we know that x double dot is equal to dx dot dt, the time differentiation of the speed, and that's equal to 0. We multiply both sides by dt, and that gives us dx dot is equal to 0. And then when we integrate the expression, we get that x dot, which is a function of time, then we need to add our first constant of integration is equal to 0. And then solving for this, we get x dot at any point in time is equal to negative c1. So we've now shown here that the speed is equal to a constant value, which we've already observed. And if we know the initial speed, then we know the speed at all times. So our equation becomes x dot at any time t is equal to x dot at time 0, so which is the initial speed. And so whatever speed it begins at is the speed that it maintains at any point in time when no force is applied to the particle. And then to find position, which is the other part of the state that we're interested in, we know that x dot, this is our speed, and this is equal to dx dt. We rearrange our terms using separation of variables, and then integrate both sides. And then performing the integration, we get x dot at time 0 times t is equal to x as a function of t plus another constant of integration. We apply our boundary condition that says that when time is equal to 0, x as a function of time, or x at that time, is x at 0. And so solving for this, we find that c2 is equal to negative x at 0, and then x as a function of time, so this would be our state at all times, is equal to x naught plus x dot at time 0 multiplied times t. And with this, we've now fully characterized the state of the system in which there is no force applied of a particle of mass m in straight line motion.